Welcome to the Explainer. So, have you ever actually wondered how ChatGPT remembers exactly what you asked it 3 prompts ago? Or how it instantly grasps the context of a massive 100-page document? You know, it's not magic. It's actually a brilliant piece of architecture. Today, we're going to completely demystify AI memory by exploring the fascinating world of vector databases and semantic search.
I mean, think about it. How does an AI find what you mean instead of just matching what you say? For decades, search engines and databases relied on old-school lexical keyword matching. If you searched for automobile, the database wouldn't inherently know to look for car. It literally just looked for those exact letters. But today, AI models demonstrate true semantic understanding. They actually grasp the underlying concepts, and understanding how we made that massive leap is exactly what we're breaking down right now.
Okay, let's dive right into this. Here is our roadmap. 1. The AI memory problem. 2. Entering the vector space. 3. How HNSW searches so incredibly fast. 4. Vector databases in action. And finally, 5. The future of AI search.
Starting with Section 1, the AI memory problem.
So the massive explosion of unstructured data and the rise of large language models pretty much broke our traditional storage methods. The tools we've relied on for the last few decades simply cannot handle how modern AI processes information. Think of the old way, a traditional relational database, like a highly organized library where you absolutely have to know the exact ISBN number to find a specific book. It's super rigid, based on exact match SQL queries and structured tables. But a vector database, it's an entirely new paradigm. It's similarity-based. It handles all that messy, unstructured data by turning it into dense vectors. Back to our library analogy, it's basically like finding a book purely based on its vibe or semantic meaning, even if you have no idea what the title or author is.
But building this new type of database introduced a bit of a villain to our story, a mathematical nightmare that researchers actually called the curse of dimensionality. Early on, developers used methods like KD trees to search for similar items. But as AI models grew, we're talking BERT, GPT, CLIP, they started mapping concepts across 768 or even 1,536 dimensions. I mean, just pause and imagine the sheer scale and absurdity of that math for a second. In geometric spaces that massively complex, distances basically become uniform. Traditional search methods become computationally prohibitive. It would literally take forever to find a match.
Which brings us to Section 2, entering the vector space.
The foundational concept solving this massive computational bottleneck is something called an embedding. These are dense, fixed-length numerical vectors where proximity actually reflects semantic meaning. Essentially, models like OpenAI's text models or vision transformers like CLIP take raw text, images, audio, the whole shebang, and transform them into these specific, dense coordinates of data.
And this brings us right to the core philosophy of modern AI memory. Information just isn't stored in rows and columns anymore. Instead, it is floating in a continuous, massive geometric space. And the golden rule in this space is that distance equals similarity. If two concepts are semantically related, say a picture of a dog and the word puppy, their vectors will be physically clustered right next to each other in this multi-dimensional space.
Now, what's really interesting here is that because this tech is so wildly powerful, a whole industry has sprung up to commercialize it. Let's look at a few of the leading vector databases making this all possible. You've got Pinecone, which offers a fully managed cloud experience, perfect if you need rapid deployment. Milvus, on the other hand, is built for maximum throughput with a really unique storage-compute separation, making it just ideal for massive enterprise scaling. Then there's Weaviate, providing a native GraphQL interface for schema-driven design, while Qdrant excels at advanced metadata filtering. And for those who just want to extend their existing infrastructure, PG Vector plugs right into PostgreSQL. There's no single dominant platform here. The choice depends entirely on your specific deployment needs.
Moving right along to Section 3, how HNSW searches so fast.
So, how do these platforms actually search through billions of vectors in mere milliseconds? The secret sauce is approximate nearest neighbor, or ANN search. See, a brute force exact search checks every single point, which is mathematically just way too slow. And algorithms overcome this by trading a tiny, often completely unnoticeable margin of precision for an absolute explosion in speed. You basically get the right answer almost instantly without sacrificing any perceivable quality. It's a real game changer.
And the absolute gold standard for ANN search right now is a fascinating algorithm called Hierarchical Navigable Small World, or HNSW for short. The way this works is brilliant in its simplicity. Honestly, think of it exactly like navigating a map on a road trip. Step 1. You start on the top layer. which acts like a fast, sparse interstate highway. Step 2, you navigate down that highway to the exit node nearest your destination. And step 3, you drop down to a denser, more local layer and just repeat the process. You move from the highway to the city streets to the local neighborhood roads, constantly zooming in until the closest match is found.
Because of this incredibly smart layered navigation, HNSW completely solves the slow scaling issues of older methods. It achieves logarithmic search complexity with exceptionally high recall. To put that in plain English, it scales beautifully, finding incredibly accurate results almost instantly, no matter how ridiculously large the dataset grows.
All right, Section 4, Vector Databases in Action.
Okay, so we know the math, we know the architecture, but how is this actually powering the apps we use every single day? Well, the most explosive use case right now is Retrieval Augmented Generation, commonly known as RAG. If you've ever been frustrated by an AI hallucinating or just confidently making things up out of thin air, RAG is the ultimate cure. It augments a large language model with a dynamic retrieval mechanism, literally pulling factual context directly from a vector database to ground the AI's response in reality.
Let's say you ask an AI chatbot a highly specific question about your company's new HR policy. Here is exactly how the pipeline handles it. First, your query is inputted. Second, that text is passed through a model to generate a numerical embedding. Third, that embedding triggers a rapid vector search in the database, fetching the top most relevant chunks of your actual HR documents. And finally, those factual chunks are prepended to the LLM's prompt, allowing it to generate an answer that is completely grounded in accurate, citation-backed context. No guessing involved.
But hey, it doesn't stop at text. Vector databases power cross-model retrieval, where text and images live in a shared space, meaning you can actually type out text to search for a specific visual image. They're also totally revolutionizing e-commerce product discovery by mapping user behavior and item attributes together. In fact, these databases are the exact reason why Netflix or Amazon seem to literally read your mind. They're matching your personal context vector against billions of items to deliver scarily accurate recommendations in sub-100 milliseconds.
Furthermore, the cybersecurity industry heavily relies on this tech. Normal user behaviors or network traffic patterns are encoded as clusters of vectors. When an incoming event is embedded and it lands geometrically distant from those established safe clusters on the map, the system instantly flags it as an anomaly. This is exactly how real-time fraud prevention adapts to rapidly evolving attack patterns without needing anyone to write hard-coded rules.
And that brings us to our final section, Section 5, the future of AI search.
The research in this field is moving at absolute lightning speed. We are on the verge of adopting learned index structures, where neural networks actually figure out the optimal way to partition data themselves, completely replacing handcrafted algorithms. I mean, imagine a world with quantum-assisted similarity search, unlocking theoretical leaps in processing speed. Or federated vector search, allowing AI to search across sensitive data silos without ever compromising privacy. We're also seeing breakthroughs in temporal vector databases that make indexes time-aware for complex financial analysis, and just massive pushes in hardware-accelerated indexing using specialized AI chips. It's wild.
Which leaves us with this final provocative thought to chew on. As vector databases start utilizing neural networks to continuously monitor query patterns and autonomously reconfigure their own indexing strategies without any human intervention, what limits actually remain for the future of machine memory? The architecture we've explored today is fundamentally changing how computers understand the world, and autonomous, self-optimizing database systems are really only just beginning to emerge. Thanks for learning with me on this explainer today, and keep exploring.